Okay, let's go for it. A few friends of mine thought that my PowerPoint presentations weren't the best, and that I should explore maybe some new media. So I've connected actually my Wacom tablet to to my computer, to my laptop, and I will show you just the notebook that I have. It's like a whiteboard. The idea really is not to present things that are like my theory on quantum physics, but more of a classical interpretation of what electrons are, what protons are, what elementary particles are, in a way you can understand with classical physics. When I say classical physics, I mean Maxwell's equations and the energy mass equivalence relation of Einstein and the Planck-Einstein relation. So let's go for it. The microphone is not great. I should buy a dedicated microphone. That's probably something that lacks in my setup. We are here. Let me choose a color. Okay. This is sort of imagine this as a ring of material. Think of the best comparison to look at things at the micro scale is probably superconductivity. You have a ring or you have some material and you're gonna apply a magnetic field to it, and then you switch the magnetic field off. So what's gonna happen is you're gonna have a pair of electrons. That's very important actually, and you have two electrons. They're gonna have opposite spin. They're referred to as Cooper pairs. If they have opposite spin, it means that they don't have a magnetic moment when you take them together. An electron always has a magnetic moment, you know that, and it can be up or it can be down. When you have a superconducting current, the macro scale, these super cooled substances, you're gonna create basically a very peculiar phenomenon, sort of a perpetuum mobile, which is impossible in normal circumstances where you have friction. But with superconducting materials, a superconducting loop, you do have a current that goes on and on and on, and it creates a magnetic field. I should show the field lines here, and these field lines, the magnetic field, are gonna keep the current in place, and the current at the same time, when you do the calculations, creates exactly the magnetic field that generates a current like that. So you have a current and a magnetic field, and the energy of the system as a whole, you can analyze it in a number of ways, but it would be the kinetic energy of these Cooper pairs that go round and round and round. I'm not sure. Maybe they're probably they are together and not at opposite sides. But electric charges repulse each other. In sort of the mainstream approach to quantum physics, you'll get wave functions, and they won't tell you where those charges actually are, but that's sort of the closest equivalent or way of thinking we have to what we have here. And this is a model of an electron. So as not to confuse you too much, I will erase the arrows. We are now here. We are looking at an electron, which we think of as a ring current. The smallest, well, maybe not the smallest, the proton is smaller. We'll talk about the proton model later. But an electron has a certain size. Everybody has seen that, from a long time ago. There's when you fire photons at an electron, you have what is called the charge radius. It's the area of interaction between an electron and a photon, and that area, that radius of interaction, is called the Compton radius. You will have heard of the Compton wavelength, but if you divide it by 2 pi, there's something like a Compton radius, and it's about 0.386 picometer. I will show you how we get there. But so that's the idea of an electron, and it's not my model. It's a model that Schrödinger invented. Schrödinger talked about a Zitterbewegung electron. He said, well, on top of the regular motion of what we think of as a charge, an electron, there seems to be like a secondary, but it's actually a primary motion of a smaller charge. We can calculate its radius. It's the classical electron radius. How do we know that? Because there's two types of scattering. When you fire a photon to an electron, you will there's two possibilities. Either the photon will mess with the electron, and then another photon comes out with a smaller frequency, so it's a less energetic photon, and then the excess energy gets absorbed by the electron as a whole, which is what we point out here. And that electron as a whole gets some linear motion, and so that's kinetic energy, and we will talk about that. I already realized that I'm getting ahead of myself. Let's explain that electron model in much more detail. So the idea really is that we do have, this thing, a ring current, and inside of that ring current, so that's the electron as a whole. I hope you can see the pointer moving, but maybe not. So I'll point it out. We have a smaller charge inside of the electron, and it's called the Zitterbewegung charge, but I sometimes hesitate to use that term. It's Schrödinger's term. Zitter is a German for a rather uncontrolled or irregular or chaotic motion. We think the motion of an electron, no, not of an electron, but of the charge inside of an electron, is not chaotic. It's quite regular, and we can discuss on, should it be a ring current model, or is this Zitterbewegung charge inside, moving in and out of the center and making all kinds of weird other trajectories. That's not very material to the discussion. The model I want to present you is just one of many Zitterbewegung models. Hestenes has a different one. Consa has a different one. They think more of a toroidal model where this charge has like a secondary frequency, but on the edge of the center of mass, of the center of charge of an electron. I want to present you the simplest models possible, which is indeed that we have a charge. It goes round and round and round, and you can actually mathematically model it as sort of a sinusoidal oscillation and a cosine oscillation. Because there's issues with the effective mass, it accelerates, goes to c and whatever, so the sine and the cosine, in any case, they're the same function with a phase difference of 90 degrees. So we're not worried about that. We really want to present just this circular motion that mathematically you can think of as being generated. And then we are here by two linear oscillations that are perpendicular to each other. Let's look at it. The first question we need to answer is, when you look at this here, a macro superconducting loop, and this here, the smallest, as David Heston has called it, the smallest superconducting loop in the universe. May not be the smallest. Again, we're looking at an electron here. Proton has a a smaller radius, much smaller, about 1,000 times smaller. The difference is, well, first we're talking about one electron, the electron as a whole here. While here in this macro model we have two. The scales are very different. Also we have, and this is fascinating, you know, and we have a material here, a ring, material ring full of molecules, because usually these superconducting materials are not like it's just iron, or it's just like a helium thing, or you know, these superconducting materials are very complex alloys. So the questions that one of the people I admire very much is Alex Burinsky. He said, like, you know, Jean-Louis, what's keeping this charge in place? You know, because there is no wire, there is no material. It's just the vacuum. It's space-time. So your theory, what keeps the thing in place? For me, this has not been a really fundamental question ever, because basically when you analyze it, what we need to prove is that the same thing as for this thing here to explain superconductivity is that the ring current, its physical structure, physical structure, that this ring current will create a magnetic moment that is just right to keep that ring current in place. Of course, we have a bit of I would say, a fine-tuning problem. We think, I mean, and that's been also that's inherent in the theory of superconducting loops, is that basically this magnetic field is quantized. So you know, you will have Planck's quantum of action in its reduced form. There's no secret about the reduced form. Either you think in terms of you know, linear distances, like a wavelength. Wavelength is basically, when you talk about matter particles, the length of the loop, and so the radius will be the wavelength divided by 2 pi. Or vice versa, you know, when you talk about a Compton wavelength, it will be 2 pi times, you know, your Compton radius of your elementary particle. Sorry, I don't want to make this too messy. It's a very messy whiteboard already. But for me, there's no problem there. So we, why not? Because, you know, you calculate the magnetic force when you bring it down to that, you know, picometer. We're not talking micrometers, but we're talking picometers. And for the proton, we're talking femtometers. You sort of say, like, okay, fine, let's calculate that magnetic force and see if there is a need for a wire. And it turns out there's not, because the magnetic force on this thing, the magnetic force is directed inwards. The magnetic field, you know, a field is something like a force without a charge to act on. But so once you have the magnetic field, which we have here, it's been shown, we have the same thing here, you know, it will go inside out, spin up, spin down, and then much smaller circulation of the magnetic field around that charge that is oscillating. Once you have the magnetic field, we know that we can calculate the force. So the main difference between a force and a field is that you know, there's a force that makes abstraction, a field makes abstraction of the charge. But so here we have the charge. That's the unit charge. plus 1 in a positron or E minus 1. And we know the force. That's the funny thing, and this is also what is a bit wrong about his analysis, is that here we have magnetostatics. There's no electrical force. When you the analysis is much more complicated. When you really get into the near fields and you say like, okay, we've got a charge moving around at the speed of light, because that's the hypothesis. I'll come back to the model. That's not really the same like a continuous ring current, where we have some charge distribution or some current, I would say a charge density and a distribution of the current over a ring. No, we don't have that. We have one charge, the zeta beweging charge, inside the small superconducting loop. So I'm doing everything away again. But so doing away with these problems, which can be solved, if you go for classical electrodynamics again, but maybe not Maxwell's equations in the way they were written by Maxwell, but going back to Liénard and Wishart. They were a French and a German physicist who really analyzed, when you're dealing with discontinuities, when you have a point-like charge, or let's say a very small volume of charge, and that little small volume of charge is either here or there, but not somewhere in between. You can solve these things. That's really the physics of the near field. But we're not going to do that here because we want to stay at not an elementary school level, clearly, not even at a high school level. But it should be possible actually at a high school level to understand this equation here. We're going to have a magnetic force that, when our zeta beweging charge goes from here to there at the speed of light, tangential velocity, v, that's sort of the tangentiality here. It's orthogonal to the radius vector. Then the magnetic force, that keeps the thing in place rather than, having that charge going in a straight line, like you're on some merry-go-round, and, if there wouldn't be like a wall or something that keeps you in place in a merry-go-round, you would just, go in a straight line and get bumped off that merry-go-round. So that's not happening. So why is that not happening? It's because, we have indeed that magnetic force pulling that thing inside, and the force needs to be equal to the change. That's Newtonian physics, and it's also correct in a relativistic sense. We have, a momentum. The momentum of this charge is its mass. We'll call it its effective mass because it's different from the mass as an electron as a whole, times its velocity, and that's going to be its momentum. And so its momentum is a vector, velocity is a vector. And the change in this vector quantity p, the momentum vector, a vector quantity has two aspects. Its magnitude, that's the length of the arrow, and then it has its direction. I don't know how to put, but let's put it here, direction. So the change, small or larger, we have a delta that goes to d in mathematics. Delta is something very discrete, two very separate moments in time or in space. When you talk about differentials, you're going to say like, okay, the the change in space or the time variable is going to be infinitesimally small. The main change in the momentum vector is going to be its direction. It's going to be this. The length of the momentum vector is, okay, this is not quite mathematically correct, but I want you to get the picture. Or in the velocity vector is not going to be its magnitude. So the velocity is always the same as the speed of light. So the momentum, the effective mass is always going to be the same. These are constants, the magnitudes are constants, p is a constant, the magnitude of the momentum vector is a constant. So the change is really direction. We have this magnetic force that goes around, that is directed inwards, but you know it acts on a charge that is moving around and around and around. So if we calculate that according to you know, classical electromagnetic theory, it's going to be, you know, what you have in the Lorentz force, which combines electric and magnetic force, is going to be you know, the magnetic force in that thing. We can write the Lorentz force. It's Q times V times B plus Q times E. So we only have magnetostatics here. No electrostatics or electrodynamics, but I said if you go to the smaller scale, we must ask that question, like, you know, what is happening at a closer range, but we're not going to do that here. We can just take the magnetic force here, and you know, here I'm going to take a bit of a shortcut. It can be shown that the magnetic force in a ring current, in a solenoid, you know, in a solenoid, something like that, you know, your typical magnet, you can show that it's going to be equal to this thing. That you know, I'm already talking for quite a while now. I'm not going to derive that that equation for the magnitude of the magnetic force in detail. You can find in Feynman's lectures or in any standard textbook. It's going to be the velocity of your charge times its momentum divided by r. So probably here I should, but you know, this slide is already quite confusing. I have the reference to Feynman's derivation of that in my papers. Just take this formula for granted for a moment and verify it as an exercise to make sure that you understand this formula is correct. If that formula is correct, then we replace V by C. And this momentum, the magnitude of the momentum vector, by some kind of concept of an effective mass. Maybe I should say something about that now. The electron as a whole has a mass that's equal to, you know, the electron mass, right? We think of it as, you know, kinetic energy plus some potential energy or field energy, you might say. Kinetic energy of that charge, to say, does it have a rest mass? No, but it has a relativistic mass. It moves around at the speed of light. So it's like, it's photon-like. I will come back to that expression because, but a photon has energy, has an equivalent rest mass. So there's an effective mass that we can associate with this charge going around and around and around. That's going to be its kinetic energy. And then we have an equivalent energy, an energy in the electric field that is magnetic field, sorry, that is real, that keeps that charge in place. That's the potential energy. So we know it's the energy divided by c squared. So in units, we don't need to worry about it. But the bottom is that we can associate an energy me c squared divided by 2 with the field energy, and we will have total electron energy times c squared divided by 2 that is associated with the kinetic energy that is associated with the theta-beweging charge, you know, going around and around and around. So we have an effective mass which is equal to the total mass of the electron divided by 2. Let me tidy up. It doesn't tidy up anymore. Too bad. Probably I did too many edits before tidying up. The velocity is c, right? The momentum, the magnitude of the momentum vector is that efficient mass, which is me divided by 2, times the velocity again, so that's c, r, and we will show that here, how we get that radius from Einstein's mass energy equivalence relation, from the Planck relation. In a moment, we will come back to that. What we can show is, well, no, let's do it now, actually. Let's go there. You think, you know, you've got a thing here, this electron with a certain energy, the energy of the electron. So it has an equivalent mass. Mass is just you know, a measure of the inertia of motion to a state of energy, to a change in the state of motion, sorry, of this whole thing here. So if you think this true, then you say like, okay, we have here mass energy equivalence. Then we have the Planck-Einstein relation. What is the Planck-Einstein relation? Well, the Planck-Einstein relation applies both to you know, a macro superconducting loop of you know, 2 electrons who have their spins aligned, sorry, opposite to each other, and it also applies to, you know, our elementary particle. Let me tidy up again. It basically says, you know, Planck-Einstein relationship, like, you know, we have a force which is directed inwards. That force acts on a charge. That charge goes around and around. So we have a force over some distance. The distance is the whole loop, of course, which is the wavelength, Compton wavelength, which is 2p r, you know, the Compton radius. A force times some distance, and then we, you know, how fast is this thing? Is it going really very fast, or rather slowly? Let me tidy up again. We will have a force over a loop, over a distance, over some cycle time. There's a cycle time, there's a frequency, and that's where, you know, we go to the Bruys frequency, what characterizes meter. But we have, you know, we have a quantity here, a force expressed in Newton times something, a distance expressed in meter, a linear distance, or in this case, you know, the circumference of an orbital loop, and we have a cycle time which is expressed in second. So we have Newton meter second. Now that's the physical dimension of h. That's also Newton meter second. So Planck-Einstein relationship basically says that you know, in nature things are going to be quantized, and how they're going to be quantized? They're going to be quantized because the energy in something like this, and then you can think about, you know, the energy as a whole. It's a, or is it a flow concept? The energy per cycle, perhaps. Case the energy per cycle, which we believe is the concept to be looked at, you know, is an energy, kinetic energy that is expended in each cycle, and there's a potential energy that renews itself or gets expended in this cycle. That's going to be equal to, it's going to be packed, so to speak, in units of h times the frequency. Now, I think I'm going to be talking all day, so I need to move on. For the proton model, we'll have something, you know, a factor 4 that we need to put here to get the radius of a proton. Why? Because we think of an oscillation in 3 dimensions rather than just, you know, a planar ring current, you know, something that moves in one plane only. But we're talking the electron here, so let's continue. Tangential velocity is, you know, when you have something going around, the velocity, the tangential velocity, will be equal to the radius of the oscillation times the frequency. So from there, you know, we get, well, let's take this one and calculate backwards. There's a few ways of going about it. But the radius will be equal, and this is what we want to know. What is this thing here? The Compton radius. Will be equal to tangential velocity divided by the frequency. Okay, the frequency, Planck-Einstein tells us, is you know, the energy divided by h. The energy is equal to mc squared. We have that c here, that remains there. So yeah, we get that a is r is equal to h bar divided by the mass of the electron as a whole times c. Okay. So we find that the magnetic force is equal to mc squared, sorry, the mass of the electron squared times the velocity of light to the power 3 divided by 2h. Where does the 2 come from? Well, the efficient mass, as said, is the electron mass divided by 2. That's the efficient mass. When you calculate that, that's a rather enormous force. 0.106 Newton. You know, a Newton is the force that gives a mass of 1 kg, an acceleration of 1 meter per second per second. So this force is equivalent to a mass that gives, to a force that gives a mass of about 100 grams, an acceleration of 1 meter per second per second. It is huge because the scale is so small. We checked it's sort of not gonna, you know, involve gravity effects, you know, a lot of mass or equivalent energy changing the curvature of space, but it's pretty huge. In any case, that's the result we have. Magnetic force is this. Now you can have a totally mechanical approach of things, which is that we say like, okay, we don't think in terms of magnetic force and stuff. We're going to think about the centripetal acceleration. So we have a centripetal force, something must keep it inside. We know it's the magnetic force. We said that, we calculated that magnetic force. But from the pure mechanics of this thing, you can calculate, a centripetal force by indeed, thinking very mechanically that, this zeta-Bewegung charge, this point-like but not infinitesimally small charge inside of an electron, must have some effective mass, and the force is going to be given by the centripetal acceleration. Now, this is the beauty of Newtonian mechanics, which are relativistically correct. These formulas, when you think about things going round and round and round, is that let me clean up. The centripetal acceleration is going to be the tangential velocity squared divided by the radius of the orbital loop. So if we replace that, we have v squared, which becomes c squared. Same thing with the radius, which we just calculated. It's that thing. It's h bar divided by me times square. So our formula, mass times acceleration, and that's again relativistically correct. What be this? The efficient mass, total electron mass divided by 2 times this quantity. Look what we get. We get the same thing here. The electron mass squared times c to the power 3 cubed divided by 2h. So this is really the beauty of the this classical or zeta-Bewegung interpretation of an electron, is that there's this was the main criticism. What keeps your zeta-Bewegung charge in place? There is no material, no superconducting material. There is no ether. There is no this. There is no that. Well, we don't need it. You will say, okay, fine, this is like an equilibrium situation, right? If we sort of give a kick to this electron sideways, then the whole thing collapses. And you are right at that. When a photon comes and mixes up, this whole thing collapses, and we have a disequilibrium state. And then the beauty of it, and that's when we're going to go to interaction, is that nature is going to restore the equilibrium state, both of the electron and the photon, let's say, by ejecting the energy that comes with the photon that happens to mess around with the electron, or the electron inside of an atomic, not an atom or molecular orbital, and it's it's going to kick that photon back out, but maybe not exactly, because the angle of attack, I would say, was a bit different. It's going to kick out a different photon with a slightly different energy and absorb, that's when we're going to come to the picture, when you have an electron moving, with this circular current getting some linear component, and then you have a photon, coming in from the side. It's a complicated situation, and that's where the fine-tuning problem of this thing is purely philosophical. Yes, of course, this thing is going to get messed up by a photon that is interacting, or by a collision with another electron at high speeds. Even if they do repulse each other, they will get near to each other. So, but nature is always going to come back to this Planck-Einstein relation, which marks a stable condition for a particle. If it's a matter particle or a light particle, it doesn't matter for all particles, and it's gonna restore the situation. The last thing I need to explain, I thought I would be explaining four slides, but I'm only gonna do one, because this one takes so long. There's a nice math for modeling these kind of orbital things. and it's given by Euler's formula, beautiful formula. Richard Feynman called it the gem of both physics and mathematics. It's this actually. We can have Euler's number, which is a rational number. It's like pi. Well, there's no other number I can compare it to. But it sort of combines, p 2 times, I would say, combined with an imaginary unit, which is nothing imaginary. It's a rotation operator. I'll put it here. Plus or minus I will I is this, and half I, 45 degrees of E, that's here, and that's E over 2. And I'm rambling a little bit, but it's sort of like imaginary unit is nothing spooky or imaginary. It's a different operation. You do multiplication, you do division, and then you can multiply a number with an imaginary unit, and it's going to be a rotation in the XY plane. Or if you want to rotate it in the XZ plane, you're going to use a different imaginary unit, J. And the genius of Hamilton was that he said, like, well, if we can think of these XY plane maybe being dynamic and J also, we know that E and J are going to be perpendicular to each other, regardless of the coordination frame. And if we're going to multiply them, we're going to have a K plane. Orientation in space, quaternions, not very difficult. At the same time, very beautiful. But it has to model a lot of complicated situations. So, any case, what I want to bring home here is that we can represent an electron by in a wave function format. E times e to the exponent plus or minus the imaginary unit times the phase. We should actually put the radius in front of it because this radius of this oscillation will be equal to what we calculated just now, HMC, so we should put that in front. For a proton, it's going to be different radius. For a photon, we're talking about fields, which can also be represented by Euler's function, but then we need to know that we're representing fields and what their dimension is. The dimensions of this cosine and this sine here, they do have physical dimensions. Well, yes and no. That's a complicated matter, but you can do derivations on them, and you can do the same thing as we did here. Show that when you apply differential operators, derivations, in regard to time, you will get sensible solutions for it. What I want to drive home is that when you do this wave function math and representation basically of what a particle actually is, there's a lot of nonsense in mainstream physics around where they say like Euler's number with an exponent minus the imaginary unit times pi, that's that's equal to -1. We go from +1 to -1, and then we have a plus sign. We go from +1 to -1. Well, the direction in which you go from +1 to -1, it matters. That's chirality. That's determines whether your spin is up or down. So saying that pi is a common phase factor that sort of cancels out in this or that transformation of your wave function or addition, that's totally wrong. The other thing I want to bring home is that we have this phase in a wave function representation of our electron. I'm going really fast here, but you can show that it's it's a frequency times t, and Euler's equation again tells us that this frequency needs to be the energy times Planck's quantum of action. So the phase argument in any representation of something that goes round and round and round is a frequency times the time. That gives you an angle. The angle is your wave function argument. That's going to be equal according to Planck's relationship to the energy, and we call it the rest energy because we're looking at this thing in a stationary space, or how you call it, when it's not moving around. And then yeah, that's basically it. And I'm gonna move to the next slide, but I'm gonna do that in a separate video and upload this one already, because yeah,